Okay, we're live.
Okay, great. I'll just wait maybe 1 or 2 more minutes and then I'll start. All right, so hi everyone. Welcome back to this series of lectures on the statistical mechanics of disordered systems. So let me start by reminding ourselves what we have done last time. So, okay, and perhaps also the one before that. So before last time we had discussed the notion of viscosity solutions, and we have seen that it's really extremely convenient to identify or at least convenient to identify the limit free energy of the standard Curie-Weiss model. And then we turn to these generalized Curie-Weiss models last time. And here we saw that there is a twist in the story because it looks as if we are having this viscosity solution thing coming backwards. You know, like we had a small parameter times the second derivative for the standard Curie-Weiss model. And for the generalized Curie-Weiss models, sometimes this thing has the wrong sign, it has a minus. And this a priori should be very worrisome because we have built the notion of viscosity solution around the fact that before we pass to the limit, we had a positive number times the second derivative. And so, yeah, this is a little bit alarming, but as I mentioned already last time, what is going to save the day is the fact that the functions we care about are convex functions of their arguments. And I already presented this statement, which I'm going to display again, which, okay, for convenience, I'm going to call convex selection principle. But yeah, like other names are welcome if you have suggestions. And the statement is the following. It says that if I have a function, let me highlight the important parts, which is convex and satisfies the equation here on a dense subset of the set where it's defined. And also if the initial condition is C1, then this function must be a viscosity solution of the equation. Okay. So yeah, before I go into this, let me like point out maybe in particular for the experts that this result will not be true, at least as far as I understand. I haven't checked this very carefully, but I don't think it's true if the H here depends also on the position, like on T and X. I think it's only working in the case when the nonlinearity is a function of the gradient. But okay, to be confirmed, but at least I'm going to use the fact that it has this specific structure. Yeah, so perhaps before I go into the proof, I'd like to propose some intuition for why this might be true. So I'm going to describe at least the intuition that made me believe that possibly this might be correct. And then, okay. So I don't claim the intuition is very good, but at least it's all I have. Yeah. So there's a question in the chat, which is very important. The convexity assumption is a joint convexity. So it's a jointly convex function in the Tx, in its variables Tx. Okay. So if you want, you know, like over the d+1 coordinates, it's a convex function. We're going to use that fact. Yeah. So I'm going to kind of talk about my intuition for why I thought this result was plausible. And I mean, basically, it's because I was not able to construct counterexamples. And when I tried to build counterexamples, you remember that this counterexample to uniqueness that we built was made by creating this corner singularity that emerges from nowhere. You know, we had this zero solution, and then we progressively start to build a corner, and then it grows and grows. And so in particular on this example, when we start to make this corner emerge, locally, if you look microscopically at when this corner emerges, what happens is that you have some place where like in some formal sense, the second derivative is plus infinity, where the corner starts to do this angle. And just nearby, you have a place where the corner, like the second derivative, formally is minus infinity, when the corner is pointing downwards. And it seemed to me that it was, at least I could not find any way to build an example in which something like this is not happening. Something where I don't have, at the same time, the second derivative going somewhat, like, to some extent in the negative direction and also in the positive direction. It seemed that it was necessary to do this, like double push at the level of the second derivative, if that makes sense. Okay, so if I impose that the function is convex, I'm not allowed to push in one of the two sides. And therefore, at least given that the statement that is displayed is true, in fact, we cannot anymore construct counterexamples to uniqueness. And yeah, it's important to stress that the assumption of convexity is not here to, in some sense, select the correct orientation for the corners. Because if I write the same statement, but I replace convex by concave, the statement is also valid. Okay, so here we're making no assumption on H. So it's just, if you fix the function being, if you force the function to be convex, or alternatively, if you force the function to be concave, then it suffices to check the equation on on a dense subset of points, and that the initial condition is C1. This is also a necessary assumption, and this is reminiscent of what we have seen in large deviations. So, are there questions on the statement? So I'm going to ultimately prove this result, but perhaps more towards the end of today's lecture. First, I would like to use it and show that using this result, we can conclude for the validity of the we can identify the limit for energy of the generalized Curie-Weiss model. So there is a question in the chat about the C1 assumption. I can really provide counterexamples if you allow me to get a Lipschitz initial condition. And it's related to the counterexample to large deviations. And if you remember, there was a counterexample to large deviations where we showed that it's necessary that this psi is C1. And okay, yeah, at least if you view it from the point of view of the Curie-Weiss model, you can build a related counterexample. But you can also build it directly from, so I haven't actually planned to include this here. So I'm going to discuss the counterexample from the point of view of the Curie-Weiss model, because I think it's perhaps, in some sense, we tie our hands a bit more, because not only do we want a counterexample to this theorem, but also one which corresponds to some sort of Curie-Weiss model. So, okay, so in particular, it will give us a counterexample to this theorem. But maybe I'll also postpone these two later. This thing is in the notes. It's at the very end of the current chapter, in case I don't reach this far today. All right. So let me start by massaging a little bit this statement so that it's going to be more convenient for us to use it. So I'm going to write a corollary, which, as we'll see, follows relatively directly from the theorem, and it's going to be convenient. So here is the corollary. I'm going to do the following. I'm going to only require that the equation is satisfied at contact points from above of the function. Okay, so let me write this. Everywhere where I can touch the function by a smooth function from above, I want the equation to be valid. Okay, so let f be a convex function such that, or maybe I'm going to write like this, f of 0 dot, which I'm going to denote as psi as usual, is of class C1. And so the assumption I do is, as I said, so suppose that anytime we touch from above, so suppose that for every tx in 0 infinity course RD and phi a smooth function. Okay, I'm not going to write the arguments, but it's defined on R plus course RD. Okay, so touching from above, I always do my little drawing somewhere in the corner. So, if f is like this and phi is like this is touching from above. So here that means that f minus phi has a, I'm going to write strict in parentheses, has a local maximum. I'm writing strict in parentheses because the statement where you write the strict or the statement where you don't write it, you can prove one from the other. It's kind of clear. So you can write it if you want. You can leave it aside if you want. Okay, so we touch from above. The assumption is that anytime we touch from above, oops, sorry, I should not have stopped the sentence. We have that the equation is satisfied. We have dt phi minus h of grad phi at the contact point is equal to 0. So here I really require equal to 0. Okay, so contrary to in the definition of viscosity solution, I was putting an inequality here, but now it's not a mistake. I really want equal 0 here. So if this is true, then f is the viscosity solution to the equation. Okay, the equation is the one we think about. Okay. Oh, I'm just saying any f you pick. So there's a question in the chat about existence of f. I'm not. I'm agnostic about whether such f exists. Okay. I mean, in truth, we could argue that it exists, but I'm not doing this. Okay. I'm just saying if such an f is such and such, then it must be the viscosity solution. Then we will see that any limit for energy will satisfy this property. And so existence will come because it's going to be a limit point of the free energy. And yeah, one remark I want to do is that, so I did my drawing in the corner like this, but in fact, it's not a proper drawing because in this drawing, the function f is not convex. Okay, so what happens when you touch a convex function from above is that you're sandwiching the second derivative is cannot be negative because it's a convex function, and it cannot be very large because you're touching from above with the function phi. So in some sense, at the contact point, you kind of know that the function is, okay, I was going to say C2 is not quite right, but essentially C2. If that language talks to you, it's kind of, it's a C11 function at the contact point. Yeah, and this will be convenient later for the argument. So that's why, that's why this corollary is actually more, it's actually nicer, because when you touch from above, you have more regularity properties at this contact point. All right, so let's prove this corollary. Assuming the theorem. Okay, I said I postponed the proof of the theorem. So I will do the proof in 2 steps. The first step is I'm going to argue that anytime I take a contact point as in the statement, indeed the function f itself solves the equation, is differentiable at this point and solves the equation at this point. That will be the first part. And then the second part will be that this set of contact points is dense. Yeah, and then given the statement of the theorem, I will be done. Does that make sense? Okay, so 2 parts. First, I want to prove that the function f is differentiable at the contact point. So let's do this. Basically, the proof is a justification of this thing I just explained in the drawing. That when you touch from above and the function is convex, it is going to have some smoothness. Okay, so let's do this. So let's say, okay, let Tx and phi be as in the statement. So I want to argue that because of the function phi, I can control f from above. So I'm going to try to make some expansion around Tx. So I'm going to try to compute T plus S, X plus Y. And okay, I'm going to compare this with f of Tx. And so the assumption is that f minus phi has a local maximum. Okay, maybe I should redo my drawing. So the drawing is here on the top right corner. So if I move a little bit and I look at the increment for f, it will be smaller than if I look at the increment for phi. So let's write it down, and then I'm going to, this is smaller than phi of T plus S X plus Y minus phi of Tx. Okay, and this is because if you rearrange this inequality, if you pass this phi to the right and this f to the left, it's just a statement that f minus phi is maximal at Tx. Okay. So that is true. And phi is smooth, so I can write this as is there? No. I can write this as grad phi Tx dot y plus partial T phi times S plus big O of y squared plus x squared. Okay, and moreover, since f is convex, I can always find a slope which is bounding from below f and which is touching f at Tx. Okay, so this I'm not going to justify, but it follows from, or at least one way to prove it is by using the hyperplane separation theorem. So let me write this. So since f is convex, and okay, so So since f is convex, there exists A in R and P in RD, such that f of t plus s x plus y minus f of tx is always larger than as plus p dot grad y. Okay, so I'm saying that you can always, I think people call this supporting hyperplane. You know, like if I give you a convex function, you can always find at least one hyperplane that is below that convex function and touches it at a given point. Okay, so now if I combine these two statements, I get that as plus p dot y is smaller than f of t plus s x plus y minus f of ts, tx, and this is smaller than so dt phi txs plus grad phi of tx dot y plus pigo of y squared plus s squared. Okay, and now maybe you start to get used to me using this sort of arguments. So forget about the guy in the middle for your y. Forget about this guy. Just look at the left side and the right side. So I have two affine functions, and one is below the other, except for this big O error. And here notice also that S can be positive or negative, Y can vary in some neighborhood of the origin as well. So this is only possible if A is equal to, if the slopes are the same. So it has to be that if you want this inequality to be valid, it has to be that A is the same as this guy and P is the same as this guy. Okay. This we have already used when we were thinking about the derivatives of the convex functions converging, if you remember. So from this, this implies that A is equal to dt phi at tx, and P is equal to grad phi at tx. Okay, but now I have sandwiched the increment of f between this affine function and this affine function, the same affine function, plus big O. So this shows that f is differentiable at tx. Oh, actually, I think later, shortly afterwards, I'm going to actually prove that there always exist these A and P. So if you find that bizarre, in fact, I think I actually give an argument that implies this actually. Okay. Okay, so f is differentiable at tx, but now we're done because once we know that f is differentiable at this point, we also know that f minus phi has a local maximum at tx. So the derivatives of f and those of phi must be the same. I mean, it's a local maximum, okay? So dt f equals dt phi. And maybe I'm going to write like this, grad f minus grad phi, and tx equals 0. Okay. And now, what's the conclusion to all this? The point is that we know that the derivatives of phi satisfy this. And since the derivatives of f are the same, the derivatives of f satisfy the same equation. This is what I wanted to show as my first step. Okay, so partial TF minus h of grad f at tx is equal to 0. Okay, so let me maybe pause for a second, scroll back up to the statement we want to show. This is what we want to show. And so far, what we have shown is that, in fact, at any of these contact points, f is differentiable and satisfies the equation. So that's interesting. But what we want in order to apply the theorem is to say that there is a dense set of points at which f satisfies the equation. So now what we need to argue is that this set of contact points is dense on the set where things are defined. Right? So let's do this. So in order to apply the theorem, there remains to argue that this set of contact points is dense. So let me write explicitly what is this set of contact points. So the set of Tx such that we can find a smooth function satisfying that f minus phi has a local minimum, a local maximum at Tx, or a strict local maximum if you want. That this is, so let's do a local maximum at Tx, that this set is dense. Yes. So I want to do this. So I'm going to fix a point, and I'm going to try to touch my function f at points which are as close as desired to this specific point. So I cannot touch exactly at any single point because you see, if the function is like the absolute value, I'm not going to be able to touch it at the origin. Okay, I cannot approach a smooth function and make it. The way I think about it is that I hover above the function with my smooth function and I lower it until the first moment it touches, and then I stop. But the way I'm going to get closer and closer is that I'm going to try to touch this point here, let's say, using smooth functions which are sharper and sharper. Like let's say parabolas which become extremely spiky. Okay, so let's do this argument. So let us fix T naught x naught. Okay, and I want to find contact points which are arbitrarily close to this point. Consider So my usual quadratic functions. Okay, I always fancy to write over 2, but it's just because I find it more natural. The 1/2 has no importance. Okay, so I think of alpha as being very large. So you see, this is my parabola, which is very spiky. And now I'm going to argue that if alpha is sufficiently large, there will be some point at which this function has a local maximum. And this point is going to be closer and closer to T0 X0 as we send alpha to infinity. Okay, so let's, just to make things convenient, let's fix a small neighborhood of T0 X0. So let V be a compact neighborhood. Let's just think of a small closed ball and define, and let's say T alpha X alpha achieve the maximum. Let's say this is, so T alpha X alpha. Let's say that this is a point which maximizes the function that I wrote on V, maximizing the function above. Oops. On V. Okay, so it's a continuous function on a compact set. We can maximize it. Now, if we are unlucky, this point is at the boundary of the domain, and so it will not really be a local maximum of the function if we don't restrict to V. But now what I'm going to argue is that as we send alpha to infinity, this point is going to converge to T0 X0, and so in particular, for alpha sufficiently large, this point will not be at the boundary, and therefore it will be a point where, without restriction on V, f minus blah 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 has a local maximum, and moreover, indeed, the point converges to T0 X0, so we are done. So to conclude, we argue that T alpha X alpha converges to T0 X0 as alpha tends to infinity. And well, I think this is relatively clear because, I mean, maybe you can take a subsequence that converges to something, and you see that if it was not converging to T0 X0, then this term here would blow to minus infinity, which is implausible. The maximum of this function on V is at least f of T0 X0. Okay, so it does not go to minus infinity. Okay, so we have, let me write like this, alpha over 2 T alpha minus T0 squared plus X alpha minus X0 squared. It is always smaller than some constant, which depends on the values of f on V. And so that finishes the proof. Sounds good? So if this sounds okay, then the next thing I want to do is to use this corollary to close this investigation of the generalized Curie-Weiss model. Okay, so I want to show that using this corollary, we can wipe out this identification of the free energy question for the generalized Curie-Weiss model. to identification. All right, so now we have to go back to the setting of the Curie-Weiss model. So there is this free energy called Fn, and so, okay, so let's say recall that we denote by Fn the free energy. And what I want, so I want to assume that Fn of 0 converges to something. And I'm also going to assume that this something is a C1 function. So we assume I'm going to call it psi as usual, the limit. So that this limit exists and is of class C1. Okay, this matches the assumption we have done for large deviations. And from there, I want to say that the limit of this Fn is the viscosity solution of the relevant equation. Right? And we know that the function Fn is convex. So we are in good shape to apply the things I just discussed. And also I recall to you that so the at time for when we fix t equals 0, we know the sequence converges. We also know that these things are uniformly Lipschitz. All of the derivatives are bounded by 1. Derivative with respect to t or derivative with respect to h. They are all bounded by 1. So by Arzela-Ascoli, we know that this sequence is pre-compact. We can extract subsequences that converge. So all that is left to do is to say that there is only one possible limit point. Okay. So by recall that by Arzela-Ascoli, the sequence Fn is pre-compact. So let F be a subsequential limit. Okay, what I want to say that this limit must be the viscosity solution to the relevant equation. Okay, and so as usual, I'm going to not denote explicitly the subsequence. Okay, I'm just going to write n and say n going to infinity, but implicitly we understand that it's along the subsequence. Okay, so I'm going to apply this corollary we just saw. So I'm going to only think about checking the equation at points at which this function is touched from above by a smooth function. So let Tx 0 infinity, of course, or G, and phi a smooth function. be such that f minus phi has a local maximum at Tx. So I'm going to, sorry, I should not use RD here. This is only one dimensional. Now we are doing Curie-Weiss. And usually I write H for this second variable in the context of Curie-Weiss. So I'm going to stick with the H. Okay, so it's really playing the same role as X, but I try to consistently always use H when we talk about Curie-Weiss and always use X when we talk about general equations. Okay, so what I want to verify, so we want to verify that f is differentiable at this point. No, sorry, we want to verify the corollary is only stated in terms of phi, so I don't need to argue this, that that this happens. Okay, this is what the corollary is asking for. And okay, so this I didn't discuss very much, but I said that if we want in the corollary, we can in fact also impose that this contact point is a strict local maximum. Okay, it's easy to fix because you can always add a little extra parabola to, so you change a little bit the test function, but you can always make a contact point be a strict contact point if you want. So I'm going to add a strict here. It is going to be useful for me because I'm going to argue that this point where a local maximum is achieved for f minus phi has an analog before we have passed to n going to infinity. So we have already used that fact. If fn converges to f, then I can find a sequence of points that converge to th such that at these points, fn minus phi has a local maximum. So there exists Tn Hn such that maybe I should converging to th and such that fn minus phi has a local maximum at Tn Hn. Okay, and recall also something that we proved last time is that dtfn minus xi of dhfn, this is bounded by c over n times the second derivative. Okay, so I want to combine all of what is written right now to conclude for this for the fact that phi satisfies the equation. So since fn minus phi has a local maximum at Tn Hn, it must be that the derivatives of fn and phi coincide at this point. And moreover, if this is a local maximum, then it must be that the second derivative points downwards. I'm only going to focus on the second derivative in H, because this is what appears in this inequality. So this relationship is valid. Okay. So let's apply all of these observations to the inequality that is displayed here. What do we get? So I compute these things at T and Hn. So the derivatives coincide. So I get dt phi minus psi of dh phi at T and Hn in absolute value. Oops. When I write absolute value, sometimes my tablet thinks I want to score, is smaller than C over N dh2. So I should write dh2 Fn, but check out that dh2 Fn is bounded by dh2 phi. Oh, I forgot to write T and Hn in this inequality. Let me add it. Oops. So here I'm going to write phi instead. Okay, by using this inequality. And now I send n to infinity, and the proof is over. Okay, so phi is smooth. So I can pass to the limit. All of these derivatives now are smooth. In particular, this guy will remain bounded when n goes to infinity. So if we multiply by 1 over n, everything disappears. And this is what we wanted. This is the end of the proof. So to summarize, we have shown that. Okay, so maybe let me expand upon my little square here. So by the corollary, this shows that F is the solution. Okay, maybe I can write the viscosity solution to make it clear. Is the viscosity solution end of the proof. Okay, this is what I wanted to justify. That so now we have said that, and we know there's a unique such solution. So we have said that any possible subsequential limit is the viscosity solution to this equation. So that completes the proof that Fn converges to that solution. All right, so I think it's a good time for a little break. I'm a little bit worried that it's been a while since I heard any questions, so I hope you're still with me. Ah, nice. Yeah, so that's a good question. So there's a question about whether the dense set of points is those points where F is differentiable. So let me comment upon this. So all of those points have to be points where F is differentiable, because this is, yeah, so maybe I have to scroll and display the statement again. So, okay, let me focus on this first theorem. when we say this, when we say the equation blah is satisfied on a dense set of points, what I mean really is there exists a dense set of points at which the function f is differentiable, and the relationship between the derivatives as displayed is satisfied. So those points where this is satisfied is a subset of a set of points where f is differentiable. But very shortly we will see that in fact you can prove without too much trouble that in fact if you know this on a dense set of points, then you know it at every point of differentiability. Okay, so in fact it is the case that under this assumption the function f solves the equation at every point of differentiability of f. And those points they are dense, but in fact they are almost everywhere, like they have a full measure. Yes, so another very good question. So I thought I would try to recap what we have proved and how it compares with large deviations after the break, but given the question shows up, I'm going to do it now. So how does this compare with large deviations? So first of all, recall that if I use the Hopf formula on this equation, I recover okay, let me write this. So reminder. By the Hopf formula, the solution to this guy is f of th equals sup over m of t psi of m plus hm minus psi star of m. Okay, so the way I stated Hopf at first yesterday was sup inf, but then you can rewrite, you can kind of hide the inf inside the psi star. Okay, so instead of writing inf and then there was something involving psi, I just write everything in terms of psi star. So it looks like this. I write it like this because this is exactly the formula we got from large deviations. And so in terms of assumptions, we have, in some sense, we have used two routes in this Hamilton-Jacobi thing. One was, let's call it the direct route, the one we used for the standard Curie-Weiss model, and which yesterday I argued is working as soon as the function psi is convex. And this route does not assume that psi is C1, like any psi will do. And this actually extends the large deviation thing. But when psi is not convex, then in this derivation we just did right now, we do assume that the function psi is C1. And this is exactly the same assumption as what we have done for large deviations. So to summarize, we have slightly extended the result when psi is convex, because we no longer require psi to be C1. And we have exactly recovered the statement of large deviations in this more general setting when psi may be non-convex. Does that? Yeah, good question. So indeed, I didn't even talk about the convexity of Fn, but so it's crucial to the proof. And I guess, so sometime long ago, I kind of mentioned in passing that the convexity of this function is valid. Yes, when we were discussing the convergence of the derivatives, I pointed out that Fn is convex, and it's true because maybe in the second lecture or something like this, a very long time ago, we observed that anytime we write, okay, what usually I call Laplace transform, which some would call log Laplace transform, that this function is always convex as a function of lambda because of Hurler's inequality. And in fact, our free energy has exactly this structure, because instead of this expectation is that I write integral of exponential of t times something plus h times something dpn of sigma, but it's really of the same form. So, and then I write log. So this is convex indeed. Okay. This is a very knowledgeable question. So I do not understand the question. So I don't know. I don't know what is this thing that is being described. So in particular, I don't know if there is a connection. Maybe yeah, maybe after the lecture you can unmute yourself and say more about this. I don't know what this is. But it's the way you describe it, at least it feels that it's stressing that the solution is not continuous. But here, this is not really the main issue, at least. This is perhaps the only very modest comment I can make. Okay, so that, yeah, so indeed that sounds perhaps relevant. So I'd be happy to hear more about this. I go grab some water, but you can continue to ask questions. So someone, let's see here. So here, it's not that I'm not saying by symmetry it also works the other side. Huh? I'm really only doing one side. And also the way things go here is it's kind of different from the definition of viscosity solution, because I only touch from one side, but then I ask that this thing is an equality, not just an inequality, as we used to do. And this is related to the fact that when you touch this convex function from one side, you're really, because it already doesn't have any space to go in the other direction, it forces it to be differentiable at this point. So sometimes there is a significant difference, right? Because if I touch, you see, in the margin I did this drawing, but this is not a good drawing because in my drawing f is not convex, and the problem is that if I try to draw a convex function, it will be smooth at the contact point from above, right? And that's why the argument works nicely. The math is nice. So this is a convex function. If I touch it from above, I will not be able to touch it at the corner in the middle. If I have a phi which touches it, maybe the phi will look like this, and the contact point will be here. Okay, I cannot really approach the singularity. On the other hand, when I touch from below, things are really different because I can really have a situation like this. So when I touch from below, I can really have contact points which are not points of differentiability. So it really, there's something non-symmetric here, right? Like we want to touch from above the functions that are convex. And if I was dealing with functions which are concave, I would want to touch them from below. And down the road, this is all to make my life convenient in order to verify this thing, right? That the equation is satisfied on a dense set of points. So in the corollary, the proof that the set of points is dense is that any of these T alpha, X alpha, any of these guys here is a contact point, right? Because if you fix alpha, then this is my smooth function, and it has a local maximum, f minus phi has a local maximum at T alpha, X alpha. So any of those T alpha, X alpha is a valid point. Okay, provided the point is not at the boundary of this V, but we argue that for alpha large enough, this doesn't happen. Okay, so any of these points, T alpha, X alpha, is a valid contact point. And as alpha goes to infinity, these points go to T0, X0. So we have found contact points which are arbitrarily close to this point I had given myself at the beginning. Thanks for the questions. I'm reassured. It's nice that I have questions. I really like it. All right, so maybe it's a good time to resume. I think now what I want to do is just prove the theorem and stop deriving consequences. But so maybe just to recap before we start. So this closes the a long time ago we decided that to set ourselves the task of recovering this result from large deviations using another technique. And right now we have achieved it. Okay, modulo proving this theorem, but that's what we were shooting for, and now we have it. Okay, and this exact same strategy is going to be what we're going to use for statistical inference. And maybe you thought that this was a kind of a hard, difficult study for a model which seems relatively modest, this Curie-Weiss model. But now we can how to say, collect the fruits from our efforts, because for statistical inference, it will be exactly the same proof for this conversion to the viscosity solution. We will use exactly the same so-called convex selection principle. And for spin glasses, okay, unfortunately, things are still to be figured out. But at least for statistical inference, it works like a charm. All right, so yeah, still in preparation for the proof of the theorem, I want to make a few observations about convex functions. So let's just take a convex function. Maybe I should let f so let f be a convex function, and let's say that u is a subset of Rd, and it's okay. I don't think I need to assume much on u, but I write it like this because I want u to be maybe R plus cross Rd minus 1, or like so maybe u equals Rd, or u equals R plus cross Rd minus 1. I want it to also apply to the case where we're thinking about this function of two variables. Okay, but it can apply to other domains. But just to clarify why I use this notation. And then we define the subdifferential of the function. So the subdifferential of f at a point x in U is given by the following. So I'm going to write this partial f at x. It's the set of slopes that give us a supporting hyperplane at x. So it's the set of slopes such that if I move around in my domain, I am above the relevant hyperplane. And perhaps the first observation, so let's say observation 1. So if f is differentiable at x, and x is in the interior of U, then this set is just a singleton, and inside this singleton there is the derivative of f. Is in the interior of U, then and this, okay, so this is not very difficult, and it's very similar to the way we argued earlier, when we were touching f from above, and we said, then therefore it must be that f is differentiable at this point. So let me scroll back up just to point to where what I'm talking about. It's just a bit simpler in some sense. This place here. Oops. This would be we have some slope in this subdifferential. Here, essentially, we're using that f is, or at least if we know that f is differentiable, it's even better than this, and therefore we identify the slopes. Okay. So that's one point. What other thing do I want to say? Yeah, there's some sort of closure property of these subdifferentials. So let me write this as well. If xn converges to x, and Pn is in the subdifferential at xn, Pn converges to P. Oh yeah, and let's say X is in the interior of U, then P belongs to the subdifferential at X. And I write X is in the interior of U because I just want to know that F is continuous at X. So the proof is you just write this relationship with Xn and Pn, and then you pass to the limit. So it's immediate. Okay. And we know that F is continuous in the interior. So that's also clear. And yeah, a consequence of this is that if I take a let's say Lipschitz. If I take a Lipschitz convex function, okay, and this time I'm going to take it explicitly defined on R plus cross RD with values in R. And if it satisfies the equation on a dense set, then in fact it satisfies the equation at every point of differentiability of F. And in fact, we have something even stronger, which is that for any Tx in R plus cross RD, we can find some slope in the subdifferential at this point that satisfies the equation. So there exists AP in the subdifferential at Tx such that A minus H of P equals 0. Okay, so let me explain a little bit what this means. So now I'm thinking of F as being, I'm kind of decomposing the variables into this T variable and this X variable. So similarly, when I think about the subdifferential, I'm thinking of it as coming as a pair with the first guy being a real number and the second guy being a vector in RD. Okay, just to match the variables which have this structure with time, comma, space. Okay, so when this is written, A is in R and P is a slope in RD. Okay. And you can imagine what this means, right? To be in the subdifferential. We will have, when we do the expansion around the point, we will write A times, let's say, a small time increment S plus P times a small P scalar product, a small space increment Y. And that's what this means. Okay, so and so A in some sense plays the role of the time derivative, and P plays the role of the space derivative. And that's why writing this makes sense. Okay, so why is this true? Let me start by arguing about this second point. Yeah, okay. So we know that on a dense set of points, the function is differentiable, and this relation is valid. So it means that there exists a dense set of points at which this subdifferential consists of a singleton. And if I call this singleton AP, then I have that A minus H of P is equal to 0. Okay. Now I'm interested in a point which maybe is not in this dense set. So I'm going to find a sequence of points in the nice set that converge to this other point. And the function is Lipschitz, so up to extraction of a subsequence, the sequence of slopes I find, I can also assume that it converges. And then by observation number 2, I know that the limit I get is going to be in the subdifferential at this point we gave ourselves. And by continuity of H, we know that the limit of the slopes will also satisfy this A minus H of P equals 0 relation. Okay, so this justifies this part. But now, if it so happens that this point is the point of differentiability, there's only one guy by observation number 1. There's only one guy in the subdifferential, and it is so. Okay, so if f is differentiable, let me write this. If f is differentiable at Tx, then the subdifferential at Tx is just the singleton made by the time derivative of f and then the gradient of f. Okay, so by the second point, we also get the first point. By this fact, we get that the equation is satisfied at every point of differentiability of f. Because we know there exists a good guy in the subdifferential, but there's only one good guy, and it's this guy. There's only one guy, and it's this guy. Does that make sense? I hope I did not lose you. So I'm going to use this fact in particular. The fact that at any point I can find a slope in the subdifferential such that this relation is valid. Okay, so let me go with the proof. So I'm going to decompose it into 3 steps. And in the first step, we verify that. So let's remember what is the theorem. So the theorem said, if we have a function which is convex Lipschitz and satisfies the equation on a dense set, and the initial condition is C1, then it must be a viscosity solution. That's what we need to prove. And the first thing I want to verify is that under the steady assumptions, the function is a subsolution. Yeah, and then I will do super solution. So to show that something is a subsolution, we need to touch from above. And as we have already seen, touching from above when the function is convex is extremely convenient for us. So this will be the easy part of the proof. But next, we have to argue that the function is a super solution. And this is the difficult part of the proof. Okay, so let's Tx Okay, so as usual, I do my little drawing. We touch from above, so it looks like this, except it doesn't actually look like this because F is convex. So in fact, F is smooth. I mean, it has some regularity at the contact point. And this is what I'm going to argue. So as before, this is really something we have already argued about. So f of t prime x prime minus f of tx is going to be smaller than phi of t prime x prime minus phi of tx. And this is t prime minus t dt phi tx plus x prime minus x grad phi of tx plus big O of t prime, t prime minus t square plus x prime minus x squared. And, so maybe I'm not going to do the whole argument again. So it's really the same as before. We know that we can touch f from below by some slope. And so this implies that f is differentiable at this point. At tx. And the subdifferential is made of only the derivatives of f at this point, but since tx is a local maximum of f minus phi, these derivatives of f or this derivative or the derivative of phi are the same. Partial t phi tx grad phi of tx. Okay, so by the observation, by this thing I call consequence above, we know that at any point of differentiability of f, the function solves the equation. And now we have said that the derivatives of f and phi coincide. So we get that partial t phi minus h of grad phi at tx is equal to 0. And this is better than what we needed to check for saying that f is a subsolution. Indeed, f is a subsolution. Okay, so now I'm going to try to venture into the second step. So now I'm going to try to, so unfortunately, I'm not sure if it will fit into 5 minutes, but almost. Let's start and see how far we get. So this step 2, I'm going to cheat just a little bit in one place. And in step 3, which probably we will do next time, I'm going to remove the cheating. Or maybe, yeah, I'll just refer to the notes. Anyway, so we give a partial proof. So we show that f is a super solution. It's a small cheat I'm going to use, no worries. So if phi touches f from below, so this is the drawing now is like this. And now this is really a legitimate drawing in some sense, because a convex function can really look like this. Then, so one can check that it must be that these derivatives of phi, so let's say touch it from below at tx, the derivatives of phi must belong to the subdifferential of f. Okay, so I'm saying that if you draw the tangent of phi at the contact point, this tangent of phi is always below the convex function. Okay, so the argument is very similar to the way you prove that the tangent of a convex function is below the function. Okay, so seeing this, it suffices to show that that whenever AP is in the subdifferential, we have that A minus H of P is greater than or equal to 0. Okay, because, I mean, a priori, what I need to check is that at any contact point, partial T phi minus H of grad phi is non-negative, but any of these partial T phi grad phi is in the subdifferential of f. So if I can show that at any of these slopes in the subdifferential satisfies this property, I am done. Okay, so this is what I'm going to focus on. So from now on, we fix this particular guy, AP, in the subdifferential of f at some point, wherever it is. And we try to argue that A minus H of P is non-negative. Okay, so we fix Tx and AP in the subdifferential and aim to show A minus H of P non-negative. Okay, so the first thing I want to observe is that by definition of AP being in the subdifferential, we have that for any T prime X prime, f of T prime X prime is larger than f of Tx plus T prime minus T times A plus X prime minus X dot P. And I'm going to try to identify, so you see, saying that AP is in the subdifferential of f at Tx means that I can touch from below with slope P at the point Tx. And I'm going to try to find the same slope at the initial time. Because in one way or another, I have to leverage on the fact that the initial condition is C1. So I'm going to try to relate what happens at the initial time with this point I'm wondering about. So the first thing I want to observe is that from this inequality I just wrote, if I look at the mapping, which from a given y gives f of 0y minus y dot p, this is bounded from below. Okay, this is just by applying the inequality above with t prime equals 0 and okay, x prime replaced by y if you want. And so I'm going to take the infimum of this function and where the infimum will be achieved will be a point with slope p. So Okay, so I'm going to, so in this step, I'm going to assume that this infimum is achieved. That's the little cheat I'm doing. But it's easy to fix. So in this step, we assume okay, so maybe I'm going to go a few minutes over time. I apologize. I promise that later I will make slightly shorter lectures to compensate, but it's really a matter of at most 5 minutes. And it would be kind of, I would be sad if I stop in the middle of this step. So sorry about this. So in this step, I'm going to assume that this infimum is achieved. And I'm going to call the point where it's achieved y. Okay, so we know the function is bounded from below, but it could possibly be that the infimum is achieved by slowly letting y go to infinity. And this, okay, we can deal with that as well, but it's just slightly more inconvenient. So just to give a cleaner proof, I want to assume that the infimum is really achieved. So in this step, yeah, this is the little cheat. So by this consequence thing that we discussed at the beginning, just before the proof, we know that we can find a slope in the subdifferential at 0p, at 0y, sorry, which solves the equation. So we know that there exists, so I'm going to call it b p prime in the subdifferential at 0y, such that b minus h of p prime is equal to 0. Okay, let me make a remark I should have said earlier. So the point of defining y as is defined now is that you have that this is true. Okay, the gradient of f at 0y is equal to p. And remember, f of 0 dot is c1. So this really makes sense. The normal gradient is equal to p. Okay, and moreover, there is this slope in the subdifferential of f, which satisfies this property. So if I think of f as being just a function of the space variable for a second, I fix the time to be 0, then in particular, this p prime is a vector in the subdifferential of f, with the time frozen to be 0. But when the time is frozen to 0, the function is c1. So there's only one possible point in this subdifferential in the space variables. And it's the gradient of f at 0y. And this gradient is p. Okay, so since f of 0 dot is c1, we must have that p prime is equal to the gradient of f, which we said is equal to p. So what we get is that bp is in the subdifferential, and b minus h of p is equal to 0. Okay, so that will be what I want to use later. And now, the whole point is to look at the mapping, which makes us travel from 0y to this point we were originally interested in, Tx. So here is the mapping. So this mapping is convex. And now I'm just going to compute the derivatives of this mapping at 0, at 1. And because it's convex, the derivative at 1 is larger than the derivative at 0. And this will give me the result. Okay, so for those who are kind of wondering when this will be over, then very soon. Okay, so recall we have, so for the derivative at 0, this is where we're near around 0y. So I want to use this. So okay, I'm going to be a little bit quick, but we have a slope which bounds from below f at the origin. And so when I compute the derivative of g at 0, I will get that it's at least as much as what is described by BP. And so, okay, I'll let you verify this, but we're going to get that this is larger than b times t plus p times p scalar x minus y. Okay, I'm just when I differentiate this object in lambda, I will get some derivatives in t and in x. And okay, if you look at okay, it's just a simple computation of the derivative. But now I also have that AP is in the subdifferential at Tx. And so when I compute the derivative of g at 1, oh yeah, and I write minus to indicate that it's the left derivative, and g prime plus to indicate it's the right derivative. But the function is just defined on 0, 1 anyway, so it's a bit spurious. So here the drawing is a bit opposite. So we are at the last point. We have this tangent here, and this is the function g. So we're going to get an upper bound on the derivative, and again, it's the same computation, but now the slopes are a and p. So we get this, and since g is convex, these two things must be compared. Okay, and I'm sorry, I said it was at most 5 minutes, but it was actually 10 minutes. So we get, so when we combine these inequalities, we get that A is smaller than or equal to B. And recall, sorry, the other way around. A is larger than or equal to B. And recall A minus, and recall B, B minus H of P is 0. So A minus H of P is non-negative. Okay, and that's the end of the proof. Sorry that I was 10 minutes over time today. So yeah, so thanks for your attention. Thanks for your patience with me. And if you want to look at step 3, where we fix this argument, where at some place I assumed the infimum is achieved, you can look in the handwritten notes, and it's done there. It's not very difficult. You just do a bit of approximation. You tilt just a little bit the functional so that the infimum exists, and then you argue that you don't make much of an error when you do this. So, no big deal.